Hello, am I audible? Hello, 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 hello.
Hello. Hello everyone. Welcome to today's session, TS session, and I hope I'm audible. So, in today's session, mostly I'll be discussing the some of the concepts which will be related to Coulomb blockade and single electron transistor, and then I'll quickly go through the Josephson effect. Then I'll discuss a little bit about the quantum Hall effect. Then I'll discuss the number of the SI system and how many base units are there and all that. So basically, these are the things that were given in the that was basically discussed in this week's by the professor. So I will try to clear those things. I know where you can face the difficulty in solving the assignment questions. So based on that, basically I will try to clear few concepts and prepared few sample questions. So and I'll answer that. So as per the instruction, I cannot, as you know, I cannot directly discuss the assignment questions. So I will try to discuss a few of the like concepts and try to clear that. So please stay tuned with me, and you can stop me anywhere if you feel any difficulty in understanding. So I'll now just quickly share my screen. So first I will discuss the. Let me check once. So where is the? Yeah, now I can edit it. Yeah, it's fine. It's working. I hope my cursor is visible, and I will mainly use this thing. It's not moving here. Okay, so the Coulomb blockade and the single electron transistor, that we need to understand, and some of the concepts which will be related to the assignment questions. So that you will be able to solve the things. I hope with this it will be very clear to all of you. So with this, I want to start. First, yeah. So it's 1 second. So Coulomb blockade is a new concept for you actually. So and the working of the single electron transistor is based on Coulomb blockade effect basically. So first, let's see what is single electron transistor. After that, we'll try to understand what is the Coulomb blockade effect. Okay. So now a single electron transistor is similar to a normal transistor, but there are some special things in this single electron transistor. So one important thing is the channel. Basically, it's this one. So this is the channel is replaced by a small dot. Okay, so that you can see here. So this one, this island that you can see, I'll rather decrease the width of this pointer. That will be better for understanding, I think. Yeah. Okay. So this part of this small dot you can see right here. So this is the part, this island. So this is a small dot basically, and this dot is replacing the channel. So there is a source over here that you can see, and drain. Okay, but this island, the small island actually is replacing the channel. Okay, and this dot is separated from the source and drained by a thin insulator. This part, and change the color. Yeah, this part is replaced. Okay, so this are the portion, this portion which separates this islands or this dot from the source and drain, and they are separated with the help of a insulator. Okay, that is mentioned here. It's changing continuously. And now electron basically when it travels from source to drain, okay, from this side to this side, when it travels an electron, so it has to tunnel through the it tunnel in two steps. So first the electron will tunnel from the source, okay, and for the source to drain, I mean in two steps. So electron will tunnel from source to drain, a source to dot, sorry, from source to dot, and then dot to drain. So tunneling will take place at two junctions. One is here, another one is there. Okay. So one junction is source to island, that is clear, and second junction is island to the drain. So this part is you can consider as positive side, and this is kind of negative. Okay. So this is some special features of a single electron transistor. This is the main important feature which makes it different from a conventional field effect, I mean transistor like MOSFET and all that. So we can define a single electron transistor in this way, that so it's a sensitive electronic device based on Coulomb blockade effect. So this is the important thing. This one basically. Okay. So we'll talk about Coulomb blockade effect in this slide, in the coming slides. So it's single electron transistor because the structure and the physics, or you can say that tunneling is designed in such a way that normally at a time only one electron basically makes it's possible to cross to this I mean tunneling junction, right? So the electrons which are traveling from source to drain, they are traveling in a very controlled way, one by one. So you can say even the, I mean, movement of it uh, carriers are controlled at electron level, right? So In so the electron here flows through a tunnel junction between the source to drain to a to a quantum dot, which is an conductive island basically, right? So quantum dot, it means source to a quantum dot, then to a quantum dot to source, due to drain. Sorry. Moreover, now the electronic potential of this island. So there is an electric potential barrier. There must be, so which avoids the movement of the carrier from source to the island, basically, and from island to drain. A normal transistor, conventional transistor, let's say, you can say there is a barrier in that structure, and also that barrier is modified with the help of gate voltage, right? So here also a barrier exists, and that is tunneling barrier. That's called the tunneling barrier, and it has a electrical potential. Electron, if you want to, if it want to cross from source to island, it must cross the potential barrier. It has to, right? So first, and then this potential barrier, of course, can be tuned by a third electrode, which is the gate electrode that you can see. So we have used a gate here. So with the help of this, basically, we can tune this electrode. We can tune the gate, right? We can tune the gate and control tuning the gate. We can basically change the barrier. I mean, this is called the third electrode. So that is the third electrode, and which tunes the potential barrier. Tune, rather, I will say, not like this. I will just tune the potential barrier, actually. Okay. Using gate. So, and this third terminal, as I already told, so just like the conventional device, which is a capacitively coupled to this island, it's capacitively coupled, right? It's a gate, so that has to be on. Dielectric in the medium, so that is capacitively coupled. That's why. So you can see here. The gate terminal is capacitively coupled to the island. So what I told you, then the working principle of silicon, a single electron transistor, depends on the Coulomb blockade effect. Remember, it's different from conventional transistor because the channel is replaced by a dot. This simply is replaced by a dot. In normal transistor, we don't have this scenario, right? And this dot is separated from source and drain by thin insulator. So that way, this dot, this portion basically is quantum confined because of the presence of insulating material on both the sides towards source and drain. The carriers which are enclosed in this island, they cannot go easily, right? So to the source side or drain side, right? So it's like a case of 3D confinement, you can say. So I'll move to the next slide. So let us now understand what is quantum dot. Okay. So here I have defined one dot. So it's shown here, and for example, you can see this small portion is a dot here, and these are the leads. Okay, basically which current can pass. With this, we can pass the current through it. So these are the leads. So you can call it consider lead one, lead two, whatever convenient. Yeah, and this gap, basically whatever gap is present here, there is a gap, right? So it shows a type of isolation. Uh, this isolation is implemented by placing here very thin insulating material. But here this insulation is shown in form of free space. So free space, as you also know, has a dielectric constant of 1 that you can consider as one of the isolations. So this lead metal, so this leads, they are separated from one, from this one, from this dot structure by this. Okay, now this dot is very small, and because it's very small, so the number of electrons which are placed in that dot is really very small, right? So this Coulomb blockade effect, it can be observed by making a very small device just like a quantum dot, right? So, and you also know what is the quantum dot, and do this 3D confinement structure. So in the 3D confined state, electrons inside this quantum dot will create a strong Coulomb repulsion. Okay, so normally in bulk bodies, there are large number of electrons present because of its big dimension, and the number of states will be very high in that bulky bigger system. It's pretty much obvious. The number of density, whatever you have for 2D, is different. It will be different and higher compared to like in 3D. So it will contain more number of states. So that way, the presence of electron that does not create much problem. But when the dimensions of this kind of dot are very small, only a few number of electrons can be accommodated. So no other kind of scattering of screening effect is present there. So whatever electrons are present there, they will create a field in this quantum dot, right? And the further movement of electrons from outside to dot, or from dot to outside will become very difficult, because the electrons which are already present here, they have very strong repulsive force. They will not allow any further, like any fresh electron to come, like from this side to this side. Okay, it's like, you know, already it's kind of in a hall effect, whatever you have seen. So once the accumulation is very much, then that will prevent further accumulation because of the same nature of the charge, they will, the tendency is to repel each other, not attract. So as they repel, so it will just simply go away and further accumulation will be prevented in the system. That's as clear as that. So yeah, and this way we can say that this device will no longer follow the Ohm's law. So, which Ohm's law states that if there is a potential difference, current should depend on that potential difference value. And if we increase the potential difference, current should also increase. But this clamp blockade, this state says even if you could increase the potential difference, current may not increase because of this dot will not allow the new electrons to come to this place. So yeah, that's the reason it's mentioned here. That is called the Coulomb blockade. So it's basically prevents further extra electron to come into the place. So as the would cost, I mean, the dot will cost too much of Coulomb energy. So that's because putting even one extra electron onto the dot would cost a lot of energy, Coulomb repulsive energy, basically, right? So and this effect is known as Coulomb blockade. Means bringing one sec. So if you now bring one electron, one unit charge, so that will also cost or needs a lot of energy. So the movement of electrons to this dot is restricted to movement. I mean restricted, and it's very difficult, right? So you know that from your like class 2 physics, that Coulomb energy is given by this expression, right? For the single, I mean, this is the for two electrons. So this much of energy you have to spend. It says that this energy is dependent on the capacitance. So if you're trying to add or like trying to bring an electron from outside to a like particular plate of a capacitor, then you need this much of energy. It's squared is squared by 2c. Now what happens? So there is a so here is a electron e charge and total capacitance c. So source and drain, right? Or the gate capacitor, whatever it is. So right now you just understand that dot have certain capacitance now. Since we are trying to make this size as small as possible, now because of the small size, the exactly, so this capacitance also becomes very small, right, as it's directly proportional to the length. So because of that, the Coulomb energy becomes very very high. So it means if you want to add an extra electron, right, to this dot, basically if you want to add one extra electron to this dot, that will cost a huge amount of energy. You need excess amount of energy, right? So here you can see, uh, here you can see how the this how the situation occurs. uh, so this is allowed energy state. So I'll change the color. So let's say this is the allowed energy. Sorry. So this is the allowed energy level, let's say, state on the source side. Okay, the source side. And this is allowed energy states on the drain side, right? The continuous energy states exist here, and because of this quantum dot, it's because of the confinement, because of strong, I mean strong confinement, quantum effects comes into the picture. And that allowed energy states in this dot, they are discrete, right, in the lead, in this leads. So the allowed energy states are in the form of continuous band. But this in this quantum dot here, this quantum dot, because of the strong confinement, quantum effects are coming into the picture, or you can say allowed energy states are discrete energy states. So electrons can exist only in this state, this state, or I mean, or in this state, right? And this much of Coulomb gap. So this is the Coulomb gap. Let's say this is, call it as delta. This much of gap is there, that is present in the system, that you can see, right? So if electron, like how to move from source to drain, it has to cross this gap. So this is the gap that on, as I was discussing. So suppose an electron has to make a transition from this side, let's say from the source side to the drain side, it has to cross a potential barrier. So also there is some probabilities associated with the transition. So it's also related to what how much gap an electron is experiencing, right, based on the gap. So suppose it's infinitely gapped, or let's say very huge gap compared to the energy level associated with the electron, that then an electron can never make the transition from one side to another side. It will become impossible to it to make a transition, right? So that's why this energy scales are very important. And uh, what systems and what are the energy we are discussing of the system and how they are related to each other, that is very important. So you have to be quantitative in those cases. Until and unless you have a clear idea about this, you cannot comment on the probability or the occurring occurring of the probability of occurring this kind of transitions in the system, right? So new basically only then new electron can be added, so if it crosses the barrier. So right now in this present situation, this state is field state. Okay, this state, I'll just rather just change the color so that you won't get confused. So this is called, let's say, the present state. Okay, this is field. This is, let's say, it's field. Array, sorry. This is field. Let's say this is field state, and this is this field state. The electron exists in this state, so we can call it this our field state. And this we can call as empty state. Okay, this we can call empty, because electron can easily move from like here to there. So that's why this state is field state, and this state on the source side, right? But uh, this is empty state because it's on the drain side, higher energy. This is higher and that is lower. So, and there is an energy gap. And I mean field state and empty state, and this is your Coulomb gap. And remember, this Coulomb gap uh, increases that. I mean, if it increases, then also the size of this quantum dot decreases. If the size decreases, what will happen? So this gap, Coulomb gap increases, right? This Coulomb gap increases if your size of the quantum dot decreases. Obviously, it means a large amount of energy need to be supplied if you want to move electron from source to this dot, right? So the same situation is shown here. Let me go to the next slide. Yeah, here is also now two stable charge states of dot with the in and in plus one electron. So this this state is suppose consider that n number of electrons are present here. Okay, so n number of electrons are present here, and if we add one extra electron, then n plus one electron. Okay, n plus one electron will go to this new state. So this this new electron, which I'm denoting as plus one, right? So this electron will go to the new state, but since there is a significant amount of energy gap, so the new electron must be provided this much of energy, okay, to make the transition from in this part to the source to the drain, like this. Now dot capacitance decreases, so in shrinking the dot, it means when we are reducing the size, this capacitance decreases, right? And since capacitance increases, that decreases this forbidden gap. I mean, this increases the forbidden gap. Further, consequently, the Coulomb energy gap increases, right? So I already explained this concept to you, and when this is this energy, so this is, let's say, u. Actually both are the same. It's e only, so it's e only, so it's same thing. When this energy exceeds the thermal energy, which is kbt, that you know, it's called the thermal energy. When it will exceed, the single electron uh, charging can be detected. Okay, this is important. Can be detected. It means normally what happens at room temperature, electrons have a thermal energy. Now, if this Coulomb energy is it's smaller than this thermal energy, there are possibility that electrons can move to this higher energy state, or you can say ki the adding of new electron to this quantum dot is not that much difficult, but at low temperature or for higher Coulomb energy, this possibility does not occur, right? At low temperature means if you reduce the temperature, this thermal energy will also reduce, and if this thermal energy becomes less than the Coulomb energy, then the problem starts, right? Then this Coulomb blockade effect will start, I mean, take place. And now at room temperature, the electrons have about 25 millielectron volts, millielectrons volt energy, this much of thermal energy, right? And if we want this Coulomb energy to be greater than this energy, then the dimension should be 10 nanometer, because this has to be smaller than 10 nanometer, because our purpose here to create this Coulomb blockade, right, is achieved when we increase this Coulomb energy beyond this thermal energy. And that is possible when the dimensions of the quantum dots are less than tens of nanometer. So at that time, this kind of Coulomb blockade is created and this Coulomb blockade seems a problem, but that is the advantage here, because it gives us an opportunity that we can control movement of even a single electron, right? So the current is controlled in that way. So it's controlled basically by the electrons, by controlling the movement of electron. So directly, so you can see here this one. I'll move to the, quickly go to the next slide. Yeah. So now look at here. So you can see here. So if we plot the IV characteristics, we can see, we can plot. So for this kind of quantum dot junction, that there is a quantum dot. Okay, let's see this. Have a quantum dot here, and then there is a metal leads here on both the sides. These are metal leads. And this is our quantum dot. Because of the Coulomb blockade, we want to add even a single electron here. So we want to add single electron from source to add from source to here from the source to the this source side from the source to this dot, basically source to this dot. If you want to add electron, then we have to basically supply the energy, right? That Coulomb energy, which is equals to the E square over Cg, as 2 E square over 2 Cg. So it's basically get defined capacitance. As you know, it's E square over 2 Cg. This much of uh, this much of Coulomb energy you need to supply to the system, right? So you can see here, and that energy will be provided by applying the suitable potential, this much potential. So that way the energy is quantized. So the energy which make an electron to jump to this dot, that is quantized, right? You can see this. So the energy is quantized, right? And you can see here, so only for a particular energy, E square over energy, we feel the I mean, that is the energy, but if you convert this much of, it will be, but in terms of voltage you want to see, right? So So 1 second, I need to. So we feel the current here in the system. So because only for that particular energy, yeah, one electron jump from this portion to this portion. I mean, from here to there. From here to there. Electron making a transition, right? So once the movement of electron is detected, we detect a current peak, right? So once we have a new I mean, and once the electron have moved to new location, again further movement is stopped. It will supply another I mean, supply another big jump into the energy. So that way the energy you can see the current peaks are discrete peaks. This one. Discrete, so that at discrete voltage levels you get the current peaks. So from the second graph you can see here the number of electrons which are added into this quantum dot. Okay, so this one, if you carefully look into this picture, the second graph, it will be clear actually. So you can see the number of electrons which are added into this quantum dot. So the number of atoms, for example, there are n number of electrons are there, and in the quantum dot now, if we want to add one more electron here, we want to make the number of electron plus one. Then this happens only when a suitable voltage basically supplied, like this. Voltage supplied as a suitable extra energy is applied to the electron here. Only then the transition will happen. So now I'll move to the next slide. So you can see here, how this single electron transistor is implemented. So this you have seen, this is your island, right? This is the island. The resolution of the picture is not that great, but anyway we need to adjust with it. This is the island. Okay, I'm re-mentioning this thing again. So or you can say quantum dot now, or this is the quantum dot, you can also say call it. Okay, fine. So this is your quantum dot. Okay, and uh, so this is the source side and this is the drain side, and this side is your okay. Yeah. So since there is an insulating layer practically in the diagram, I show you there's a gap, right? But practically it is implemented with the help of an insulating layer. So because of the transition of the insulating layer, I mean this one, you can just consider this is the insulating region, and also I'd rather change the color. And okay, with the help of the insulating layer, right? So there is a capacitance here, that is in the left junction. I mean, this one is the left junction capacitance, and another is the right junction capacitance. These are the capacitance that we have. And there is a right junction capacitance. So between this island or quantum dot and the drain, right now a gate. So you can see in between this, so there is, in this pathway we have introduced a gate terminal. This one basically is also placed here, right? This one CG, this terminal we have introduced here. And that gate terminal introduces one another capacitance that is called the gate capacitance, right? So the single electron transistor is composed of the two tunnel junction. uh, this one junction is the second quantum tunnel junction, and along with one island which are capacitively coupled to the two electrode, right? So, and to get electron, sorry, this island is capacitively coupled actually to this gate electrode. And so this capacitance is shown here, and the gate voltage is shown here. This is the gate voltage, right? This one is the gate. This is the gate voltage. This is the gate voltage, as I already mentioned, and this is the gate capacitance. It's written here. So this island is coupled, capacitively coupled to source and drain with the help of this junction capacitance. And the gate is also coupled with the help of the this gate capacitance, right? So this island is located in between two tunnel junctions with capacitance Cl and Cr, that is shown over here. So this single electron transistor can electrostatically be controlled by this gate capacitance. Of course, it's shown here, and the total capacitance of the island is now a left side capacitance, right side capacitance plus the gate capacitance contribution from the three sections, and such a setup is called the single electron transistor. Okay. In conclusion, we can say this thing, right? So this is it, and I'll move to the next slide. And these are the advantages of the single electron transistor. So this is the low energy consumption, high sensitivity, the compact size, as I already mentioned. Its operating speed is also higher. The simple principle of operation, the straightforward co-integration with the traditional CMOS circuit, right? So these are the things. So next, I will quickly discuss the Josephson effect, right? As per this thing. Okay, let me move there. Okay. So this is very important. Like Josephson phenomena and effect is very important. I mean, effect in the field of superconductivity, you can say. So how we basically get a Josephson junction? So basically, I think it has been already taught by you. It was taught to you by the instructor, and I'll just, for the sake of remembering this thing, just to give a touch, and I'll repeat. Like when we have, let's say, two superconductors on both we have two superconductors. When we bring them very close together, I mean in a very close proximity, if we bring them, because of the wave function overlap, uh, a supercurrent will flow from one superconductor to another superconductor between a weak link, right? So this current is completely dissipationless. So because of the flow of this current, we do not get any kind of voltage that is developed in the circuit. So that means V is zero. So that means its resistance is zero for this current. That is why it's completely dissipationless, and it is called as a supercurrent. Okay, so this supercurrent, as you one second. So this is the supercurrent between the superconductor. It is defined as IC times sine del phi. So this del phi is the phase difference between two superconductors. Okay, so this del phi will completely depend on the phase on both the superconductor. I mean, this is simply just the phase difference of the two superconductors. So here we are simply connecting to I mean we are bringing them close together, but we are not applying any voltage, that you can see here, right? So this is the first Josephson equation for this scenario. I is equals to IC times sine del phi. So this will happen only when barrier is very small. Okay, the barrier is very large, this electron cannot tunnel. So what happens basically, not a single electron are doing this. So according to BCS theory, a Cooper pair has been formed. So Cooper pair is basically a bound state of two electrons. Okay, so this can flow as a Cooper pair. So and we get a supercurrent. So here the phase coherence is very important for the flow of supercurrent. So if the system size is comparable to the like comparable to the sorry comparable to the system size, only then this I have shown to you already. So this has to be comparable with the system size. Otherwise, phase of the superconductor will be completely destroyed. So why it's very interesting? I mean, you can simply, so let's see, it's a macroscopic phenomena. Though you know the quantum phenomena is microscopic, and we talk about the nanoscale, but what is happening? You can describe the entire superconductor simply by a macroscopic phase. So the whole superconductor can be described as a single phase. So once, I mean, the phase is preserved here. So for the, let's say the superconductor one has a phase, macroscopic phase phi 1, and this is the, and another superconductor has a phase of phi 2. So simply the difference between two phases of both the superconductors is giving you the phase difference, and that will decide the flow of supercurrent between two superconductors through the weak link. Okay, so this is the beauty of the this Josephson effect. So you can simply describe the whole superconductor by a single phase. So now as a two, so this is the typical IV characteristics uh, of the Josephson junction. Okay, so I could have plotted the I in the x axis and V in the V along the y axis, but I did ulta anyway. Just for the sake of understanding, it's fine. But anyway, so what is happening? See, so I have mentioned, I have introduced another parameter, IC, right? So what is IC? IC is just it's basically called as critical current. So critical current means, I mean, the maximum current that we can have in the Josephson junction. So as you know, the sine phi cannot be greater than 1, right? So of course this is the maximum supercurrent that we have in the junction. So that's just IC. So this is, this I is your external bias. This is not internal. That we are, I is something which we are applying from the outside, and it's like, it's like you just connected the whole thing uh, via a battery. So you are putting in this thing in some external bias. You are basically applying some external bias, and you are just simply driving the current through the system, and you are just characterizing how the current inside the system is changing, and how the voltage has been, most voltage is getting developed, right? Based on that we have the IV characteristics. So what is happening here? So see, so there, I mean, within this region, I mean, let's say consider the just one quad one quadrant here. Let's say we are increasing the current in a positive direction. So as long as we are within the limit of IC, we can see there is no voltage has been developed in the circuit. That means the V is zero. So V0 indicates the resistance of the Josephson junction is zero. So supercurrent still exists. So we are in a supercurrent state condition. But the moment we cross this IC, I mean, if we further increases the external bias beyond IC, we'll see the voltage will start building up in the system. That means it will enter into the normal state. So once it switches out from the superconducting state, we define that condition as a normal state, right? So that's kind of the switching from a superconducting state to the normal state. Normal means it's purely resistive. So it can be metallic state or whatever. So it means so V and I will just following the Ohm's law, and like it's pretty much, it's pretty resistive system, right? So that's why it's normal. And another condition, another thing, like let's see, there are a lot of parameters. Just by tuning all this, you can simply switch the whole junction from a superconductor state to normal or vice versa, right? So another parameter, as I mentioned, it's the just the junction length. So one parameter here is just the external bias. So see, you have two parameters in your hand. First one is the external bias. Another thing also, you have like a magnet. You can also apply magnetic field, and you can completely destroy the whole the whole uh, symmetry and the whatever superconducting state. You can simply drive it out from there. And also the temperature. But the key factor, what I mean, we are here discussing is, first one is the bias, and second one is the length of the, I mean, the junction, I mean, the size. So if we make the junction in such a way that the size of the junction is very very greater than the phase coherence length which is associated with the system, then also you cannot see any supercurrent. Because the superconducting phase, the phase which is associated with the superconductivity property, will be completely destroyed. In that situation, you cannot expect a supercurrent to flow through the system, right? So this is the another thing that I have shown here. So see, so I will show you how it look basically. Now basically, also we are using some kind of gate here in the system. So let's say we can have a system of junction of niobium, aluminum oxide, niobium. So this is the another Josephson example of an Josephson junction. So there are two Josephson effect that we can see. First one is the DC Josephson effect. Another one is the AC Josephson effect. So what I basically mean by DC Josephson effect. So as you can see from the IV characteristics, right? So now it's kind of inverted and easy to understand, because now I've switches this thing to, I mean, I is along uh, again, I mean, there is a confusion because don't get confused. I is basically your independent parameter over here, and V is basically dependent. So V is just a function of I. Okay, so that's how the IV will look like. So basically, the red solid line indicates when we are sweeping the external bias from the, let's say, the forward direction. This is called the forward sweep. So you can see the path that, and the blue solid lines is basically the backward sweep. I mean, if you see, consider, okay, first you are going from 0 volt to 10 volt, then you are coming back to, I mean, rather I'll say from 0 to some nanoamps current you are providing, and then from higher nanoamps current to you are going back to 0 nanoamps. So that's how the forward and backward thing has been established over here. And basically, so you can see here, right? So when we are sweeping the our bias in the forward direction, the path that the IV characteristics is following, not the same path is being followed when we are sweeping it back. So this is, it's clear there is some hysteresis, right? So this is the hysteretic behavior we can see in the IV characteristics of this Josephson junction. So when it sweep it back, it stays in the resistive state for a longer time and then switches back to the superconducting state. So basically, junction is retrapped back to the superconducting state. So this is a non-linear effect in the junction is going on that you can see. So now I'll discuss very briefly how the Cooper pair has been formed here. Okay. So this you can see. So where I was mentioning this Cooper pair formation. So it's like a mechanism under reflection. It's like a mechanism through which electron can enter into the superconductor, right? So in this process of pairing, I mean Cooper pair formation, charge is always conserved, and the energy of the Cooper pair is zero. Where you can see, so if one electron is entering here, so another hole has to be, I mean, to conserve the charge, another hole is has been generated and reflected back into the system, and Cooper pair has been entered into the superconductor of charge 2e. So this height of the potential barrier in this gap is delta. So the electron will have a energy which is less than the barrier ka height. Then the electron cannot make the entry into the superconductor. So I'll just quickly discuss the AC Josephson effect. That is very important because, and also please listen carefully because some of the questions can be related to this effect. So if you understand this concept, you will be able to easily solve the assignment, some of the assignment problems, and further and the future problems as well related to this Josephson junction. So this is the equation that is here. It's called the second Josephson equation. So you can see here is a time dependence, right? Exactly. That's what actually it makes it. I mean, this is the thing that makes this equation different than the fast Josephson equation. So in fast Josephson's equation, the phase was constant. If you carefully see and go back to the first Josephson equation, you will find the phase was not evolving with the time. So that's why the supercurrent was, I mean, whatever was flowing, that was completely dependent on the phase difference at a particular moment. And then that point of time, supercurrent is constant. Also, the critical current was defined, right? So then the phase was not evolving. But what happens now if we I mean, if we just provide a voltage externally and if we drive the system, I mean, now what is happening? Uh, Basically, we are applying a voltage here. Okay, let's say plus V. So that is a radio frequency voltage. I mean, that's a sinusoidal AC voltage that we are applying. So let's say at t equals to 0, we apply a voltage V. Phase difference will start going linearly. Okay, so that you can see from this Josephson equation. So what they have established, so this rate of change of phase difference is directly proportional to the applied voltage. I mean, E and H, so obviously those are the fundamental constants, but mainly it's proportional. I mean, it's changing linearly with the applied voltage. And the rate, I mean, the slope, that is 2 EV over H cut. So you can see it's the beauty. I mean, you can take either aluminum junction, graphene junction, nanotube junction, whatever, but the phase evolution will only depend on the fundamental constant and whatever voltage we are applying. It's completely blind to whatever we are uh, material we are using. This effect is universal. I mean, it's insensitive to the material that we are using. It will only depend on the fundamental constant. That's the beauty of the Josephson effect over here. So Josephson junction is simply a resistor, basically above the critical current that I've mentioned. Now under some finite voltage V, we have the AC supercurrent. Now what I mean, the supercurrent will be modified, right? So now it will become the function of time. I mean, the moment we start applying the voltage, so it's no longer the phase will stay constant and the supercurrent will change with the time. So now this is the modified supercurrent, that is IC sine of del phi of t. It will start oscillating with time. So now basically all we need is to measure. I mean, after applying the voltage, we need to measure the current. But there has to be some detectable current, right? I mean, if we can't detect, then there is no meaning. To detect this thing, I mean, if we apply some random voltage, we cannot detect. So to detect, we have to apply a radio frequency voltage. Only then you will see the IV characteristics will become a staircase. So it will give you a staircase like IV. So that is called the Shapiro step. This is the most important part of the AC Josephson effect. Then you will see the IV of this thing will be a step like this thing. So this is called the Shapiro steps, and the radio frequency that we are applying is equal to 2 EV over H cut. Okay. So now we need to calculate the Josephson. You can also calculate the energy. but just integrating from 0 to t, just a product of supercurrent times the voltage that you are applying in the time domain, right? So that will give you ej times 1 minus cos phi. So this is the important thing. Another parameter which will define, which is defined here, it's called the Josephson energy. It's basically the scale of energy. I mean, maximum energy that is given by the supercurrent IC. That's why it's called the Josephson energy. It's also proportional to the supercurrent. Okay. Now let's think about a realistic Josephson junction. So this is the Josephson energy. That's so far so good. And now if the junction is very small, I mean, the thing is, we cannot have a ideal Josephson junction in the reality. So along with that, I mean, along with the Josephson junction, we always have some capacitive contribution as well as the resistive contribution. Once we try making a Josephson junction, so it will also come simultaneously in parallel, right? So that's the thing. I mean, that's the thing when we talk about a real Josephson junction. So this will also come simultaneously in parallel to the JJ. So now let's say if the junction is very small, so the other energy will also start dominating, like the capacitive energy. So the CJ will be higher, right? No, CJ will be very. Sorry, this is actually I've done a mistake. So if the junction is very small, yeah, actually CJ will be higher. Okay, fine. Huh. So CJ, for the small junction. So what this is what the modified Hamiltonian is. Okay. Now let's uh, focus on this portion. This is the Joseph. This is your Josephson junction. This is your Josephson junction. Fine. And this is the resistive, and this is the capacitive contribution. Okay. So this is called the RCSG model, resistively capacitive shunted model. Shunted means because it's in parallel configuration. That's why it's shunted. And this model is called RCSG model. So now what we have, instead of simply IC times sine phi contribution, we also have the resistive contribution as well as the capacitive contribution in addition to the uh, Josephson junction contribution for the real Josephson junction, right? So this is your Josephson current, that is IC multiplied by sine phi, the Josephson supercurrent, and this is what this seems to be non-linear, right? This is of course non-linear term that we are dealing with, and then the resistive component comes. It means V over I. Current means V over I. V over R, resistance, I'm voltage divided by resistance. So from this second Josephson equation, if we replace the V over that thing, so if we will simply get H over 2 ER times d phi dt. This is a normal current and resistive current, right? And then the capacitive current, I mean the displacement currents come. This is because of the charging, the static charge that we have on the plate, both the sides of the plate, and that because of the capacitive effect, we have this kind of current. So we just need to differentiate once again. I mean, if we take the time derivative of the, I mean, second time derivative, I mean, it will become del 2 phi del t square. That is why of the second Josephson junction equation, sorry, then it will give you a second differential equation like this. So then this is the total current. So if we now simply rearrange, I mean reconfigure this thing. So what I mean will end up will have end up will end up having something like which will look like this. So you can see now it's a phase, right? It's a second order derivative. It's a first order derivative of the phase, and this is in the sine phi. You can also approximate. I mean, in a small angle approximation, this will give you simplified. Or if you can also do the Taylor series expansion of this. So what is interesting over here? So now if you carefully look into the equation, you will find this is nothing but related to what we have for the simple pendulum. So it's like a particle in a washboard potential, right? So here I is, I mean, the your external current bias, that where an particle of, I mean, particle is basically can be thought of as a phase here in analogy to that. And so it is kind of analogous to the, I mean, particle. So you can consider phase. I mean, there we consider as a theta, I mean, right? For the pendulum, it's the same thing. It's a particle instead of particle. We have only phase, the superconducting phase. Where, as I already mentioned, you can always describe a superconductor. That's why it's a microscopic phenomenon. Though we are describing the whole thing using a quantum mechanics, but still, this is the beauty of the Josephson effect. You can simply describe the whole superconductor just by uh, using a term called phase of the superconductor. So this is the typical potential profile, and this is how the particle moves depending on what potential has been provided, right? So this is in analogy. This is very important. Please note it down. So this will help you to solve any future problems and associated with the Josephson junction. So this is mainly related to the RCSG model and how this is related to how we can relate this kind of thing to a classical problem. It's up close because simple pendulum is nothing but it comes under classical mechanics. No longer it's quantum, but there is the beauty is hidden. I mean, we can also uh, compare this thing with the quantum mechanical phenomena and the terms and parameters which are associated with it. That we can also like relate just by converting, just by multiplying few of the parameters, like some of the universal constant like h to e. So you can simply convert this to thing. So here mass of the like the capacitance whatever we have, that can be thought of as a mass of the system in the simple pendulum, and the resistance is basically the friction coefficient, and the external force obviously it has to be uh, has to deal with the external bias only. And this is the your plasma frequency of the system, which is related to your Josephson energy. So these are the thing. I mean, why we have hysteresis. I mean, there are two situations. So once we discuss about 1 second. So there are two scenario like overdamped condition and underdamped condition. These are very a bit advanced thing. So what is happening? I mean, in overdamped situation, you cannot have, you will not see any kind of hysteric behavior in the IB characteristics, and in the in the overdamped situation, basically region, you won't see any kind of hysteresis. But in the underdamped situation, whatever I have shown you, there you have seen there is a hysteresis in the IB characteristics that was present there. So it's about how uh, the capacitance of the system is, how the friction coefficient, the capacitance, how the supercurrent is, and all these things will also play a very important role. So that is why, I mean, you can go through this and have a look once. And as I already mentioned, the Sapphire steps, it's in the radio frequency range. This is what we have in the gigahertz. So as I mentioned, the real Josephson junction will always have some capacitance and resistive contribution. So that's why it is. So this is it. I think whatever I mean with the Josephson junction I wanted to discuss, that was it. And you can just go through it once more, and yeah, you will be able to solve all the questions yes, accordingly. So now the last topic that I want to discuss today, the some SI units that I'd like to discuss with you. some of the basics. I mean, this is from the 10th standard physics, but still, for the sake of uh, solving the assignments, you need to revisit all those things again. So, if you have any questions, you can ask me. Mm, we're almost at the end, but 1 second. Yeah. Yeah. So, SI unit, it's basically it's international system of measurements, right? So basically, I mean, that are used universally in technical and scientific research to avoid the confusion with the units, right? So having a standard unit system, it's important because it helps the entire world to understand the measurements in one set of unit system. So there are some there are some units which are called the base SI units. So these are very primary. So I'll just discuss this thing one by one. So first one is your length. Okay. So we define this by L, and you know it's the unit is meter, SI unit, and symbol is M. Then the mass comes. Earlier we also like only in our time also you it's about it was MLT, right? I'll discuss. So it's like it's the unit is kg and time. So whatever time is the second. So it was mostly about MLT, but there are also some units and the quantity, also some physical quantity is there that cannot be composed of using ml and t. So whatever quantity that you can like whatever m to the power x, l to the power y, and t to the power z. So this is like whatever you are going to get, that will give you a compound or let's say derived units, right? Like force, as one of the example is force, right? Force is nothing but kg meter per second square. It's mass time acceleration, right? So it's like it will be, if we discuss, it will be ml t to the power minus 2. But there is some also, these are, that's why these are not fundamental. So you can compose the thing just by using the primary unit, uh, like mass, length and time. But other than that, so mass, other than the mass, length and time, we have some other quantity, physical quantity, that cannot be composed of mass, length and time. So there are some four other units that we have also. Those are also called the base units. Then we have the, this is the first one, this is the second one, this is the third one, and the fourth one is electric current. Fourth one is the electric current. Its unit is ampere. Okay. Then also we have the temperature of the system. Temperature of the system, we can call it theta, and the unit, SI unit is Kelvin, right? Another two base units are also has been recently added. It's like amount of substance, yeah, amount of substance, which is the unit is mole. Okay. And the last one is the luminous intensity, which is the unit. In short, the symbol is candela, right? So these are the best units. So total 7 base units we have, but we have also 22 derived unit, which can be easily derived using, can be derived, can be derived using 7 base units. That's why they are called derived units, right? So if we just simply discuss what are the some of the examples of the derived units, we know the force will come, the force, capacitance, right? Capacitance, frequency will come, resistance, and so on. Okay, list is very long, and you know that. So this is how it's defined. Okay, this is the SI unit system, and now I'll quickly discuss the quantum Hall effect in graphing. Okay, it's also another thing that will help you to solve some of the questions in the assignments which was recently given to you. Quantum Hall effect in graphene. Okay. So the quantum Hall effect in graphene is quite different from that in the two-dimensional electron gas, right? And it's quite interesting example to consider because the electron spectrum of graphene resembles those of relativistic particles, right? So on the relativistic particles, you have this particle, antiparticle, so as a function of momentum, right? So first I'll write this E plus minus for particle and antiparticle is function of momentum. It's basically the wave vector. This is in the context of relativity. Keep in mind, okay, because we are dealing with some particle which has a speed close to speed of light, mc square plus h cut ck square. Okay, and of course we have not applied any magnetic field over there, so it's b equals to 0. The probability particles in the non-zero magnetic field, the spectrum become quantized. So when we have uh, magnetic, when we'll have a spectrum, I mean, let's say under some finite magnetic field, this will be modified like this. So it's a function of the like index of lambda levels, and it has a following form. So there is a mc squared, of course. This is from the rest energy. Then you have the same plus then the quantized part, this 2n h cut eb c square at p not equals to 0. Okay, so the derivation is quite involving actually, and basically consider the Dirac equation in the magnetic field. From there you can easily derive. So in graphene, what happens, the rest mass is 0. Okay, in graphene the rest mass is 0. Then we use this replacement. So this c becomes your Fermi velocity. This kind of conversion that we need to do. This Fermi velocity will come of the order of 10 power 6 meter per second. So if we see the spectra of, like, if we see the E versus K, so it will be like this. As you know, velocity is like simply dE dk in the back, I mean, in the K space, right? So that's how we define our Fermi velocity and all that. So it's d dk, it's about the energy dispersion relation, and we get the velocity out there. So and the spectrum then becomes for graphene E plus minus, then also has 3 plus minus sides. N Vf square root of 2 nh cut E B, right? And there are several things to note. The first one is that n is equals to 0 when have a zero slant, when I have a zero slant down level index, that is equals to 0. That's quite I mean, this is quite different. It's very different from the two-dimensional electron gas system, right? Different than two-dimensional electron gas system. Therefore, if you consider the simple harmonic oscillator energy levels, then simply you have the n plus half h cut omega, right? You have a 0 point energy over there because of the simple harmonic oscillation. All the energy states are quantized, and you cannot have a zero energy over there because there is a minimum energy that is half h cut omega, and n is restricted only for the n is here integer that can only either take, I mean, from 0 to 1 2 3 4 so on and so forth with the interval of 1. So that's how it works. But for the two dimensional electron gas system, but not for this one. So it's non-zero energy, right? In the but in graphene zero sand system, zero energy. Then the second one is the energy is under the square root of p in graphene. And in 2D, it's proportional to b. And the other one is root n, right? Is the Landau level index. But for 2DEG, what is happening? E is proportional to n, right? That's the that's how it differs. Fourth one is nothing but the degeneracy, right? So here you have two spin, two valley for graphene. So it's 4 degenerate. 4. Now we can write down this in terms of the degeneracy, right? So the filling factor, this is called the filling factor, is the carrier density times Planck constant over EB, right? And the lambda level, so at n equals to 0, you will have fourfold degenerate zeroth lambda level, right? It's centered at e equals to 0, and carrier density is also 0 here, and it has to be separated by the filling factors nu plus minus 2 for in order for it to be symmetric, right? So we can draw this on the density of states, I mean E energy versus density of states. So this is, let's use 0. There will be the energy level. So the zeros, this is the 0 lambda level, and then we'll have, I need to erase this part, like this and this, okay, and so on. We'll have some other lambda levels as well, na? So the first one, this is a 0, then below to that we'll have -1, -2, above 0, +1, +2, +3. These are the index for the lambda, for the different lambda levels. These are the indices, of course. So and so on and so forth. So, but if you, when you draw them on the carrier density scale, so using this NS, the 0 Landau level would actually be separated by this plus minus 2, as I already mentioned. So if we have, let's say, filling factors of this kind, proportional to the density, I mean, carrier density. This, for examples, the rho xy, the resistivity, just to see the quantization. But sorry, I have to use sigma. Rho stands for the resistivity, but I want to plot with respect to, I mean, how it will be the case for the conductivity. So for that, I need to I need to write sigma instead of rho. So that's not, yeah, 2 minus 2 will have the plateau, right? So it will be like this. in the conducting region like this. 1 second. I'll draw it better. Yeah, so this Plato's will be this is 1/2. 1 second. Then the next level, right? The next filling factor. And so on and so forth. So the quantum Hall effect in graphene is half integer in the units of conductance of the quantum, right? So I'll rather write the statement so that you can. So the quantum Hall effect in graphene is half integer in the units of conductance quantum, which is nothing but 4 of E square divided by H, right? It's like half, 3 by 2, 5 by 2, and so on. Always plus minus, yeah. So this is the thing. That's all about the quantum Hall effect in graphene. Okay. So just go through this carefully. I hope you will understand and you will be able to solve most of the, I mean, rather all the questions which was given for in the recent assignments. And okay, so sounds good for this week, and I'll again meet you in the next week, next Saturday, same time. Okay, see you. Bye.